Welcome to Ask and Learn.
Okay, so down in the denominator, we have exponential growth, and up top, we just have sine of 2n. So intuitively, this should be clear that this is going to converge, and it looks like it's going to converge fast. Looks like it should converge fast enough that it'll actually converge absolutely. And sometimes it's easier to prove absolute convergence than it is to just prove regular convergence. And if you are able to prove absolute convergence, then that implies regular convergence as well. So that's going to be the approach that we're going to take here. So it starts with just the intuition of, assuming that this is going to converge pretty hard enough to where it just converges absolutely. And then the observation that absolute convergence in this case is going to be something that is easier to show. It'll be easier to show because when we take the absolute value here, whoops, this shouldn't be equal. We should be getting something that's less than 1 over 1 plus 2 to the n, right? Because sine can't get any bigger than 1. And now this is something that looks much nicer to work with. And then we can do another inequality here. Replace this 1 plus 2 to the n with just 2 to the n. Because remember, if we replace the denominator with something smaller, we're going to get something bigger. So that's what's happening here. 2 to the n is smaller than 1 plus 2 to the n, but since it's in the denominator, we ended up with something that's larger. And then we know that this is finite. So this is finite, and all of these terms are positive. So all of these terms are positive, and we're bounded. So if all of our terms are positive and we're bounded, then it means that we have convergence. Okay, and if we have convergence of this thing, well, that means that we have absolute convergence. And if we have absolute convergence, then that implies regular convergence. So absolute convergence of this guy gives us regular convergence of this guy.